Welcome to this DP Physics video summary on the high-level topic of 11.2 power generation and transmission. So how do we generate power in our society? Well, basically the principle is the fact that we have a rotating coil in a uniform magnetic field, or rotating magnets in a coil, but in this example we have a uniform magnetic field strength B, and we have a coil here. The black line is a coil which is rotating anti-clockwise with a frequency omega, which is 2 pi times, or an angular frequency omega, which is 2 pi times the linear frequency. And remember, omega is in radians per second. So as the coil rotates around, there is a change in magnetic field and therefore magnetic flux. That's the green curve here. And because induced EMF is the rate of change of magnetic flux, the induced EMF, or the voltage time curve, looks like this. In this case it would be a cosine function, where the induced voltage or the induced EMF is omega NBA cosine omega t. Now you're not given that formula in the data booklet, so it could be good to know that the peak voltage omega 0 is given by omega NBA, where omega again is the angular frequency. Now because V equals IR, the peak current I0, remember subscript zeros stand for peak values in this context, is the peak voltage divided by the resistance. But because we can't take an average of a cosine function, we have to use what's called root mean squared, or RMS values. So the average, or the RMS current, is the peak current divided by square root of 2, and the RMS, or average voltage, is the peak voltage divided by square root of 2. Now in these systems we have power generated, electrical power, because we have mechanical energy being converted to electrical energy, and the maximum power is the peak current times the peak voltage, and the average power, P bar, values with a bar on the top of them signify averages, is a half times the peak current times the peak voltage. Now it's important when we transmit or transfer electrical energy from one place to another that we don't lose very much energy, and that's done through the use of transformers. So a transformer is a soft iron core with a primary coil wrapped on one side and a secondary coil wrapped on the other side. And because magnetic flux is transferred through the iron core, if we have an induced EMF in the primary coil, we also have an induced EMF in the secondary coil. And by having a different ratio of coils in the secondary coil to the primary coil, we can either step up the voltage, therefore stepping down the current, or stepping down the current and therefore stepping up the current again. So the ratio of the number of turns in the primary coil to the number of turns in the secondary coil is equal to the ratio of the induced EMF in the primary coil divided by the induced EMF in the secondary coil, which is equal to the current in the secondary coil divided by the current in the primary coil. Note that the circuit symbol for the transformer looks slightly different to the schematic. So by stepping up the voltage, we step down the current, therefore reducing power loss, because power is proportional to the square of the current in the wire. It's also sometimes important to be able to convert from alternating current to direct current. When we alternate current, we go from a positive to negative values of the potential. And when we've converted from AC to DC, we say the wave has been rectified. And we can either do that with a single diode. A diode is a component which only allows current to pass in this direction. In that case, we say the wave has been half rectified, we lose the negative bits of the wave. Or we can construct a so-called diode bridge with 4 diodes, which allow, when the current flows clockwise, the current will flow through this direction through the resistor and then out again. And when the current flows anti-clockwise, it will flow the same way through the resistor and then out again. In that case, we have this voltage time curve, and we say the wave has been fully rectified. So this shows full wave rectification. Note that to find the period of oscillation, you have to go between 2 peaks.